Hello, everyone. I am Katherina Xagorari from the Athena Research Center, and I will be presenting Curex, the recommender system that we have in inode. So it is natural that we want our recommendations to be smart and help the user. So when a user asks a question in SQL to a recommender system, we want the recommender system to take some things into account. First and foremost, we want the system to understand what the user is interested in. In this example, I want to look for the company name, so naturally this is what I'm interested in, but I'm also interested in some specific filters, like I want the expenses to be more than 2K, and I also want the revenue to be above 3 million. But I also want the system not to make assumptions about how knowledgeable I am about the data. I want the system to understand that maybe I'm not so sure what I'm looking for. So for example, this query could return few to none results, and I want the system to steer me in the right direction. So taking all these things into account, we would have nice and interesting recommendations that would be interesting to me. So here we argue that data spaces require a data spaceship. And why is that? Well, data nowadays are large and they become increasingly more complex. Users cannot always know the structure of the data, and navigating alone in an unknown data space is inefficient. In this example, as you can see, we have the human perspective that might be an astrophysicist, and they really understand this picture, and this is familiar to them. This information is very well known to them. But to acquire this information from a database might be very complex. This here in the right, we have what might be the computer perspective, that the information is spread out to multiple tables and the user might not be, it might not be easy for them to acquire this information. Thus, we would only want the user to have some intuition about the data, and their question should be enough to begin their navigation. So the data spaceship we propose is called Curex, and it is composed of two components, an offline and an online component. Offline, the system is analyzing the data space and it builds a navigation map for the user. And online, when the user asks a question in SQL, the system will consult the catalog, the navigation map we mentioned, to guide them to regions related with their question. So let's see how this data analysis is done and how is this navigation map created? Well, we can think of this large database as a data space that is accumulated of subregions formed by attributes of tables in this database. So offline, the system will locate interesting information in dense regions with unsupervised learning. Then it will form SQL conditions that lead to these subregions called clusters, since we are doing unsupervised learning. So for example, subregion 1 might be enclosed in a two-dimensional space where the attribute 1 is less than 18 and the attribute 2 is more than 40. Lastly, it will keep a catalog of these regions and their corresponding columns and tables. Now, online, it's time to generate these recommendations based on the catalog that we mentioned. First, we get the query from the user. For example, the user wants to select attribute 1 from table 2, where the year is equal to 2018. Now the system will search its catalog for entries that include the column attribute 1 in the select clause from the table TBL2. If it does find this information in its catalog, it will reform the user's query to guide them to these regions, and it will also rank the recommendations based on relevance to the user's initial query. So going back to our first claim, let's see if the system managed to produce smart recommendations. In the first scenario, we pose the initial question where we want to see the company name from the table companies where the expenses are above 2K, and they also have a revenue above 3 million. So now the system judges and evaluates this question, and it says that, okay, it's not too selective, it's rich in data. So now I will also expand your question by keeping your original filters, and I will also propose that you focus on an area that the zip code is less than 1440 and above to 2020. Okay. Next, in another scenario, I will pose another question where the establishment year is equal to 2018. But now the system actually evaluates that I'm not so sure that there are many data there, and it's too selective. It might have only 2 rows. So now the system will assist me and propose that I look into other regions. It will discard my initial filters and propose others, like establishment year being less than 2020 and more than 2010. So now it's time for the demo. Once again, we're in the open data dialog of inode. To begin our navigation, suppose that I'm a project officer investigating the contribution of the European Union to certain institutions. In order to make a fair decision for future project funding, I will be looking for institutions and the sum of each contribution in descending order. The interpretation best suited to my search is the first one. Find institutions and the sum of contribution of participant members of these institutions grouped by the names of institutions. Sort results first by the sum of contributions of participants in descending order. By clicking on the recommendations button, I will get recommendations generated by the recommender system in inode. As you can see, I am presented with alternative queries related to my initial question. I will focus on the first one. Find institutions and the sum of contribution of participants whose contribution is less than or equal to 1 million. For participant members of these institutions grouped by the names of institutions. Sort results first by the sum of contributions of participants in descending order. I will focus on the SQL equivalent first to understand how this recommendation was generated. At the top is our initial question to the system in SQL. Select institution's name and the sum of each contribution from institutions table and project members table. As we can see, the recommender system built a similar SQL query with an additional filter. Here, down below, is the additional filter and the recommendation equivalent in SQL, where the EC contribution is less than or equal to 1 million. The recommendation, therefore, focused on a specific range regarding the EC contribution. The system, a priori to my question, located an interesting subregion in the project members table that is enclosed in this range of the EC contribution. If we were to interpret the results, we can see that although its individual contribution inside the database is less than 1 million, Fraunhofer has accumulated most of the contributions in this example. Finally, the resulting institutions and the sum of contributions, as well as their distributions, are shown here.